Okay, so the next talk in this session is by Matthew, who will tell us more about robust constant time cryptography.
Hello. As Colin said, I am Matthew. I'm a PhD student at UC San Diego, and this is joint work with a number of excellent collaborators. Today, I want to tell you a story about this, namely that constant time is an insufficient formal model for cryptographic code. And first, I want to take a brief digression and preach to the choir and talk about why formal models. So one main reason is to provide increased assurance in systems, but I think that it's sometimes underlooked is that we use formal models to guide and justify rules of thumb for those developers and engineers who are not so familiar with the formal models and tools for building them. Cool. So next, let's talk about what is constant time. So constant time is a property designed to ensure that code, typically cryptographic code, does not leak secrets. Importantly, constant time, as you might guess from the time in there, also includes through timing channels. So as a very simple example, let's look at this very fake code, which takes in a key as an argument, does some computations on it, in particular does two different branches, one that does something slow, another that does something fast. As you might guess, these two things operate in different amounts of time, so therefore this can leak information through a timing channel. To capture this formally, we use a non-interference property where we consider two keys, and then we must have that the function called on these two keys has the same set of traces, and these traces we abstract over the specific timing to capture events that sort of capture more abstractly that the two things have different times. And we can see that for this example, if we have the key 0 and anything else that isn't 0, then these things will not have the same traces. One of the really nice things about constant time is it provides a bunch of rules of thumb for developers in order to be able to develop their code to be constant time. And the first of these, which is violated here, is that you do not branch on secrets. And the other two are we don't use secrets as pointers and only use constant time operations. Returning to our thesis for this talk, let's take a look at the end of this. We say constant time is an insufficient formal model for cryptographic code. So what is cryptographic code? Let's take a look at a slightly more real function, which was simplified from the libsodium library. This is part of the stream cipher implementation using salsa20 underneath. And let's take a look through our rules of thumb at some real code. So firstly, don't branch on secrets. Here's the only branch in this code. It's based on constants. We're good to go. Second, don't use secrets as pointers. That just doesn't happen in here. Also good. And then I promise you that salsa20 does not use any non-constant time operations on secrets within it. So we're all good to go. So let's take a step back and look at this line here. This is nothing to do with constant time at all. And so we're going to return to that. But first, let's talk about the reality of cryptographic code, which is this is not actually the model of what cryptographic code is in the real world, because cryptographic code is based on sort of a principle of don't roll your own crypto. Cryptographic developers write libraries for others to use so that end users and application developers are not implementing crypto badly, which means that our model looks something more like this, where we have a library, such as libsodium, that is used inside of a larger application. Unfortunately, in the constant time model, keys are just arguments to these functions. But the reality is that these keys live somewhere in memory, which means that constant time relies on memory safety, as something like a buffer overflow would just leak that key no matter how constant time the stream function is. And I'd like to argue that developers are actually thinking about this, returning to this memory 0 function. What was this doing? And in libsodium, they actually use these secure memory zeroing functions to clear the temporary secrets in their implementation, as otherwise a buffer overflow could potentially access those. And further, these keys live at rest in memory, and libsodium provides a number of guarded keep functions to securely protect the keys at rest. Excellent. So you might notice that there's this little thing that's like, I'm a buffer overflow. Well, why don't we just write our apps in Rust? And you should absolutely do that. Unfortunately, in this modern age, the security researchers went and found Spectre. And Spectre breaks all of our assumptions about memory safety. And further, it also breaks a lot of our constant time rules of thumb. And this is a big issue for dealing with when we care about Spectre and actually getting secure cryptographic code. So then here's the model with constant time, where we just have a function on its own and this property. So how do we instead provide properties that can support what cryptographic developers are actually doing? And so I argued that we need to move to this application model, where we instead have a robust constant time property that takes into account that these are libraries running in a larger application. And then the library must be secure when linked against this application. By moving to this model, we are able to do things like model attackers, such as read vulnerabilities or buffer overflows or Spectre, and further provide new rules of thumb justifying things like the memory protections in libsodium. And then lastly, we use this model to design a compiler that will guarantee robust constant time. So the rest of the talk, I'm going to look at how we define robust constant time, look at Spectre and how it plays into this story, and then last talk a little bit about our robust constant time compiler. So let's look at defining robust constant time. So for robust constant time, as I said, we have this picture now where we have a library and an application. So we're going to need to model both of those. So let's start with the library. So we define libraries based on an API, a set of function names, and further a set of secrets context, such as keys or whatever, that captures which secrets that library will use. Libraries then are just implementations for these API functions, which may use within them the secrets. On the application side, applications are simply open expressions E using functions from those library APIs. So you may think of this as just gamma entails E. So E are these open things. Further, we have defined this in a lambda calculus with a block-based memory model, where access beyond the end of a block is used to model overflow, and this, in the semantics, gives a non-determinate deterministic access to another block. Further, to model what developers are actually doing, we provide memory protect instructions into the semantics that locks a block of memory. Cool. So we now have these two tools. Let's look at how we actually define robust constant time. In particular, we start with a library with a fixed API and set of secrets, and then we consider for all applications that library may be plugged into in pairs of keys. We plug the library into that program. Then we must have that whole thing on the two keys has the same set of traces. If so, the library is robustly constant time. Excellent. I want to focus in on this one little line here, for all applications E. The reality is this is not actually how the real world works, once again, because cryptographic libraries are used in many different contexts, such as C applications, Rust applications, etc. And as such, library developers are working with different sets of assumptions. Are there read or write gadgets? Do they have to worry about buffer overflows in the application? Are they on a speculative processor? So returning to our definition, and how do we capture these different attackers? So far we have a definition that is robust against all applications. To capture attackers, we then restrict the set of contexts or applications that we need to consider when linking against, based on what assumptions we make about the application. For instance, buffer overflows or Spectre. To capture these application assumptions, we capture actions that the app can or cannot do. So we begin with our sort of most general model. The general unrestricted context is essentially modeling memory unsafe applications. They can do essentially anything. A slightly more realistic model is that developers are actually worried about is where there are read gadgets somewhere in the application. Memory can be read, but we can't do quite so many attacks. And then lastly, something like Rust can be modeled by a memory safe attacker, which may not take any of these sort of untoward actions. And later we'll talk about how Spectre fits into this picture, sort of slightly, mostly being in that middle bubble. Formally, I told you about how applications are simply open terms E, which means we have still a problem with trying to define these these properties and assumptions about the applications, which is I cannot run this program. It is a hole in the middle of it, and we get to that hole, we are stuck. So our idea to handle this is assumptions on the application must hold for all well-behaved libraries. Essentially, if you put our well-behaved cryptographic library in there, then the application should run there. When we're looking at this formally, we separate, plugging this in, separates the run of the whole program with a library plugged in into a trace that has back and forth between application calling into the library, calling into the application again, returning, et cetera, et cetera. And then, for instance, for defining memory safety, we said that there's no essentially out-of-bound behavior in the application. So what this looks like is we require that when the application is running in the trace that there are none of these out-of-bound memory accesses. And then we call into the library. Here we may assume that the library is well behaved. So we assume that there is no out of bounds behavior. And then once we return to the application, assuming that there was no out of bounds behavior in the library, we now require this no out of bounds again from the app, and et cetera, and so forth. So now to define robust constant time with attackers, and for instance, for the memory safe robust constant time, we simply define for all applications that are memory safe for all well-behaved libraries, and then our definition continues as before. Read-only being defined similarly, and we'll get to Spectre a little bit later. So we have a new model. Let's look at what it is useful for, and let's in particular turn to justifying some rules of thumb, such as the mem0 in this. So before we had these constant time rules of thumb, they were very useful for developers, but let's look at why we're doing this and should we be doing this. And in particular, we develop a set of rules of thumb for read-only attackers, which we believe is what a lot of cryptographic developers are concerned about. So firstly, we say you should allocate your keys in protected memory, as we saw with the libsodium things. So you should lock down the keys at rest. You then have to toggle this memory protection across calls into the library, so we allow access only while we are within the trusted cryptographic library. Third, constant time does not go away. We still need this function to be constant time. If it leaked secrets, then all would be lost. And then lastly, at the end of the function, we must clear all temporary secrets. And we are currently proving that this set of rules of thumb, when expressed more formally, give you robust constant time against read-only attackers. Excellent. So next, we're going to take a look at Spectre. So we have lots of tools for being memory safe these days. A lot of them work very well, and I recommend you use them. Unfortunately, Spectre exists. And to back up and sort of explain Spectre for those of you who are not familiar with it, Spectre is based on modern processors guessing which branch to take and other sorts of things within the processor. So for instance, you have this very simple code. You have an index that is attacker controlled. We check that it is less than the length of the array, and then we access index into the array. And so what an attacker can do on modern processors is pass in a bunch of things that are indices that are within the array, and everything is good. It's that the processor goes like, this check is often true, so let's just go ahead. If an attacker then passes something that is well outside the bounds, the processor has sort of been trained to assume that the condition will be true, and just says, okay, just continue executing. It's been true the last 20 times, just keep going. Unfortunately, this means that we temporarily are running code where our assumptions are violated and can access other parts of memory, such as where a key is stored. And the sort of problem with this is that while the processor eventually realizes its guess was wrong and rolls things back, there are traces of the wrong path which can leak this information. As such, Spectre breaks all of our existing assumptions about memory safety, even in things like Rust. And in particular, applications are no longer memory safe. And as I mentioned earlier, it also breaks our constant time rules of thumb, and cryptographic developers can no longer rely on these rules of thumbs that we've developed for them. So to sort of work this into our model, we define a notion of speculative robust constant time. And it works out that Spectre is actually very related to having read gadgets in the application in terms of robustness properties. And to do so, we define a high-level speculative semantics for our language, which lets us compare to our other attacker models. We capture the essence of Spectre at a high level with a speculator that is sort of an oracle parameterized over where speculation occurs. And this lets us capture a number of different versions of Spectre all in one model. Speculative robust constant time is then just robust constant time in the speculative model parameterized over some class of speculator. So let's take a look at trying to provide some rules of thumb for speculative attackers. So we said these are related to the read-only attackers. And in particular, we have the same protections that we want. So we still need to allocate keys in protected memory and toggle memory protection. Further, we need to not only make cryptographic code constant time, but speculatively constant time where it might be still running with some sort of Spectre gadget within it. And lastly, we must clear all temporary secrets, but this now is extended to a sort of wider range of secrets, such as registers. But let's return to this, because for those of you who are familiar with constant time or Spectre, that was a very non-useful statement to just say, make it speculatively constant time. So recall that our constant time rules of thumb were things like don't branch on secrets. The problem is now things like this, where we're just doing something on a constant, may end up actually being skipped and leaking information through getting access to different parts of memory, and everything just goes awry. So I want to just very briefly talk about very speculative ideas that we are just beginning to work on and would love to hear feedback on about what are some speculative rules of thumb for providing speculative constant time. So first, we think that it is to develop a form of speculation-aware CFI, or control flow integrity, that ensures that essentially our control flow within the library is something that we can actually, once again, make assumptions about, and then have some way to prevent speculative leaks. This one we actually have a little more information on. This is things like speculative load hardening or fencing, etc. Cool. So I'll try and go through the rest of this and get us back on time a little bit more. So lastly, I'd like to talk about our work on a robust constant time compiler. So we have a number of different attacker models, and they have different protections for them. Unfortunately, there's no one perfect solution that just protects against all of these. And what happens now is that library developers are hard-coding these assumptions in and making just one choice. For instance, this memory zero and other stuff that libsodium does. Unfortunately, there are things where this is a problem that is known, where this is an issue where libsodium, someone pointed out that the memory barrier in their mem0 doesn't actually protect against speculative attackers. But they then closed this because they're like, protection against Spectre would be a significant slowdown, and it's not always needed, so we're not going to do it. We're making trade-offs. To solve this, we propose a parameterized robust constant time compiler that pulls the choice out of the code, and instead you just get to choose who you're concerned about, which attacker, Spectre, or otherwise, and then we add the appropriate memory protection, clearing, etc. And right now we say, just bring your own constant time. If you provide us constant time code, we'll just wrap in the protections, guarantee you robust constant time. And separately, we're working on some Spectre protections to provide speculative constant time as a way to implement that. And currently, we're working on a proof of robust constant time for this compiler. To conclude, we argue that constant time is insufficient for how cryptographic code is actually developed. Changing to a robustness property captures the reality. This lets us provide new rules of thumb and give the basis for building a robust compiler. So I hope I've convinced you that robust constant time is a realistic formal model for cryptographic code. Thank you.
We have plenty of time for questions.
Hi, Ralph Jung from ETH Zurich. In this example you had about read gadgets, you were like, there was the function doing something on the secret, and then at the end clearing it all out. Now, probably in this program, there's going to be other threads that will run in parallel, and so they might be reading the secrets before it's been cleared. Is there something people do against that? Is that something your model can capture? Like, how does this change the game?
Yes, so this very much does. And so here, different sorts of memory protection mechanisms act very differently. For instance, Intel's memory protection keys, MPK, if you're familiar, actually provide thread local memory protection. So you can essentially only provide access to this memory region for just one thread, and others still cannot read it. Whereas something like Linux's memprotect does not have such protection, so other threads will still be able to access. So we do not have, without something like MPK, we don't have as good a solution for that.
There first.
You have been talking about speculative CFI. Do you have any idea on how to implement that, software, hardware?
So we both. We have some ideas for both, and so we have sort of a very new idea with, I forget the exact, but in some new Intel hardware that lets you do essentially checks on a condition, and then if that condition does not pass, just wipe away the state of all registers. And so with some pre-computed information about the control flow graph, we believe that this will let us do essentially if the jump was to this block was not supposed to occur, we just blow away, and occurred speculatively, we blow away the state of all registers, so there is no access to the secrets. And then it can continue operating speculatively, but there is, once again, no secret information, so it's fine. So that's one idea, and we have some other thoughts on how to do this in software.
Marco?
So I guess my question is, so when you were talking about speculative constant time, which kind of speculative leaks do you have in mind? Like control flow only?
So for speculative constant time, the ones that we are focusing in are Spectre V1 or Spectre PHT, so leaks through branch conditions, and then also extending this to Spectre V4, I think it is, for the branched BTB. So where speculation on where branches go may occur.
So do you also plan to tackle like Spectre STL or general value speculation?
STL is not currently in our thoughts at the moment. No, and nor a value speculation. There are models that sort of capture those, but that's in what we're building. We're not looking at those.
Yeah, I also have a question of my own, if no one else. And it's related to the memory unsafe attacker.
Okay.
And you mentioned that you want to model it as some sort of non-deterministic read or write to some other memory block. But in general, that's still not enough to capture what can happen on memory unsafe operations. If I can also say write over the return address,
Yes.
or over pointers. So, and then get complete control over the program.
Correct.
So how do you get around that? Will it also have CFI there, or
how do we like protect against that?
Yeah, how?
So I can sort of answer like in 2 points. Like how do we model that? So in my opinion, the model sort of captures this in that we are a robust property. So there essentially like exists another application that does the like essentially has a function that it can pull from memory in the model and like execute that function. In protections, memory unsafe is something that we actually think is almost a little too unrealistic for these sorts of circumstances. If you're like in a context where you're completely memory unsafe in an application, it's not a particularly realistic model for. It is essentially like more than the cryptographic libraries should really be concerned by. At that point, you have just bigger problems.
Okay, so you're saying that it's too strong an attacker
Exactly.
model for this.
Yes.
Okay, thank you.
Yeah, and you could do things with like full process isolation and things if you actually cared about that, but that is not our focus.
Okay, so let's think this